Hi, I'm Adam. Welcome back to Godot Game Lab. In this video, we'll implement Slay the Spire-style map generation, which is honestly probably one of the most anticipated features in the whole project. So you can see when I start a new run here, we have this map generated for us. I can scroll with the mouse wheel up and down, and we have different kinds of rooms. Boss rooms, campfire rooms, shops, treasure rooms, and these little knife icons which are representing regular battles. And when we start the game, we can select any of these starting points to start from, and when I click on it, we actually go into the battle scene, where we can play the battle as we usually do. And when I finally win this battle, all the previous functionality is still there, so I can collect my rewards, add new cards to my deck, and continue onward. And you can see that this little line here indicates that I visited this room earlier, and I can no longer click on this one or either of the adjacent starting points we had before. There's only one place I can continue, and that's playing another battle. And after winning another battle and collecting the new rewards here, you can see that this one is highlighted too, and I have two rooms to choose from when I continue my journey here. If I click on the shop, I go to this sort of placeholder scene where the shop will be later on, but if I go back, you can see that I can still continue on. The campfire is still a placeholder too, but I can go back and continue all the way up to the top here. Also, if I close this run and start a new one by running the scene again, you can see that there's an entirely different layout generated again, but while the layout is distinctively different from the previous one, the proportions are kind of the same, right? Most of them are battles, we have some shops and campfires sprinkled in. At the middle, we always have the treasure rooms. And at the end, we always have a campfire preceding the boss at the very top. So without further ado, let's see how we can actually make this in Godot. Before we implement anything or even discuss the algorithms we use to generate the map, let's talk architecture first, like we usually do. In terms of resources, we have one new resource called room. The room basically describes a room in the map, and it has the following properties. A type, which is an enum. Is this room a campfire, a shop, a boss room, etc. A 2D position, which is the room's coordinates in the 2D game world. A grid position, which we'll come back to when we discuss the algorithms. An array of rooms called next rooms, so we can keep track of the rooms we can go to from the current room. And last but not least, a status flag, which we'll use for interactivity. This can either be selected or unselected. The architecture itself is pretty easy. The map depends on the map generator, which will do the heavy lifting of actually generating a new map. Of course, for the map generator to work, we need the room resource we just discussed, because the map consists of interconnected rooms. For the map itself, there's nothing really new here. When we click on an unlocked room, we use the event bus to emit the map exited signal, so the run can show us the correct view. If we click on a campfire, the run changes the current view to the campfire scene, right? Pretty straightforward. So why don't we discuss the algorithm we'll use to generate the map next? One really cool person on Reddit recommended me this article, which is a super nice and in-depth guide on how the map was actually generated in Slay the Spire. So the author was referencing the source code of the actual game. So it's as close to our base material as it possibly can be. The article itself starts by showing the map layout and discussing the terminology they use throughout this whole article. What's interesting to us here is that the map layout itself is basically a grid which consists of 15 rows that they call floors and 7 columns. After generating that initial grid, the next thing to do is to randomly pick some different starting spots at the bottom, meaning floor 0. And after having our starting points, we start generating the different routes, which are indicated with different colors here. And we need to make sure that generating these routes adhere to some rules. For example, no paths can cross each other. And what that exactly means is something we'll come back to later when we actually start coding, so I can show it to you visually. After we generated the routes themselves, we can start assigning different room types to those nodes, right? And here we have some rules too. For example, the rooms on floor 0 are always battle rooms. And then we also always have treasure rooms on the 9th floor. And finally, on the last floor, before the boss room, we always have campfire rooms. And as for all the other rooms remaining, we can use a random weighted distribution to randomly assign types to all those remaining nodes. Mind you that here we also need to adhere to some rules. I won't go into details with all the rules here because we will discuss them anyways when we do the code. And basically that's it. When we're done with all the steps we discussed in this article, we have our map ready to go. So with our project open here, we could start implementing the map generator itself. That's the most interesting part, right? But before we can actually do that, we need to remember what we discussed in the architecture overview. Namely that the map generator itself depends on having a room resource. Why? Well, because if you think about it, the whole map is an interconnection of different rooms, right? So let's start by creating this room resource. And to do so, let's expand the custom resources folder in the file system, right-click on it, create new script, and the name will be room.gd. And let's make sure that it inherits not from the node class, but from the resource class instead. Press create and double click on room.gd to open it up in the script editor. So let's see how we can build this room resource, right? First things first, we need a custom class name called room. Then we'll have an enum for the type of the room, which can be not assigned, monster, treasure, campfire, and so on. This will determine what is in that room in terms of gameplay, right? Then we'll have a bunch of export variables similar to what we discussed in the architecture overview. So each room has a type, which is a value of the enum. Then it has something we called grid position, which is a row and a column number, because if you remember the article, the whole thing is in a grid, right? So a row and a column index sort of identifies where the room is in that grid. Then we have a vector2 position, which I refer to as 2D position. So this is an actual coordinate in the 2D game world, so we know where to put that room in the map. We also have an array of rooms, which we call next rooms, so we can store which other rooms we can go to from the specific room we're currently in. And last but not least, we have this flag or boolean variable called selected, which is either true or false, and we use it for interactivity so we can keep track of if a room was selected previously or not. And then for truly debugging purposes, we override the toString method, so we have a string representation of a room resource. Why do we need this? Well, because when we're finished with the map generator, we want to test it, right? But we won't have access to any visuals, right? So these rooms won't have icons, you can't click on them, there won't be connecting lines between them yet. So the problem is we don't have the visuals to test it, so we kind of have to test it in the console, right? With printing out stuff. But the default string representation of resources is just the name of the class and the unique resource ID. And that's not really useful for us. So if we override this, we can actually test if the map generation works or not from the console. And for the rooms themselves, we'll display the column number and also the type of the current room. And in order to make it prettier and to make sure that all these rooms have the same length of characters, I wanted to use only the first letter of the type enumeration. So this bit of code might be a bit confusing, so let me break it down to you. So let's say we have something similar here, right? We have the same enumeration, and in the ready callback in this little sandbox playground here, I created a variable, which is an enumeration of the same type, and it is type shop, right? So each room will be assigned one of these values. The first thing you need to know is that actually enum values and variables are integer numbers under the hood. So basically I said type.shop here, but what it really is it's a number. So if we take the whole enum, not assigned will be 0, monster will be 1, treasure will be 2, campfire will be 3, and shop will be 4. So if we take a look at the first print message here, it says 4. So even though we say type.shop here to make our code more readable, under the hood, these are just integer values. It's something that's good to know when you're working with enums. So the next thing here is calling type.keys. And what this does is it takes all these identifiers from within the enum and return them as an array of strings, right? Like so. So in the next step, when we already know the type of our room, we can get this array of strings, and because the enumeration itself is an integer, we can use that index to actually refer back to the identifier itself as a string. And what I mean by that is that this variable, if I print it out, it will just print out 4 like so, right? But if I use this type.keys and grab the element with the index of type, we can get back this shop string we have from the array of identifiers we have, right? So in the last step, we make sure that all the string representations of the room have the same length. Why? Well, because when we write these debug print messages in the console, it will be much easier to keep track of the rooms and the connections if all the rooms have the same character length. And so what we do here is we take the string, for example, in this case, the shop, and only grab the first character of that string. And that's perfect here because if you look at the different types we have, all of them have different initial letters. So having access to the first letter will be perfectly fine to distinguish between the different types. So this is what this piece of code does. I just wanted to clear this up a bit because it might weird look at first. And basically that's it for the room itself. We can save this with Ctrl+S and move on to the map generator next. And to start creating the map generator, let's go back to 2D view and open up the map scene by pressing Ctrl+Shift+O and searching for map.tscn. And here what we need to do is to select the root node, the map node, and click on the plus sign to add a new child node or press Ctrl+A. And this time we'll be using a simple node, so search for node, add a new child node, double click and rename this to map generator. And then we need to attach a script to this, so click on the attach script button, make sure that the name stays Pascal case, so everything is consistent with the conventions, and make sure that we use the object empty template here, so we don't have auto-generated code. Click on create, and buckle up because this is going to be a long one. So let's see what we need to do here. First of all, we'll provide a custom class name called MapGenerator. Then we'll have a bunch of constants here. Let me explain them one by one, but I also want to say that you can experiment with these values if you want to use different ones for your game. This is where we can really configure how our map generation works in the game. So what are those x distance and y distance constants? Well, let's imagine that we have our grid here, right? These are all rooms we can use. We have the floors here vertically and we have the columns here horizontally, right? So we have all these rooms and visually we want to sort of have control over the space between them. So x distance will be the amount of pixels that we use as a gap between the two different rooms horizontally. And the y distance in a similar fashion is the distance or the gap between the different floors, right? So we say that this distance should be 30 pixels and this vertical distance should be 25 pixels by default. Again, you can experiment with those values. So we have our grid or map here, but it kind of looks rigid, right? If the distance is the same between all the different rooms. And what we do is we have a placement randomness constant, which gives us a leeway so we can sort of randomly move those rooms around a bit. And by a bit, I mean 5 pixels here. So the maximum randomness we can provide to these positions is 5 pixels. And if we apply a random value between 0 and 5 on the x and the y, we get something like this, right? It looks a bit more interesting, more organic, and elevates the whole map to another level. So we have two new constants next, called floors and map width. Floors is basically the number of rows we have in this grid vertically, which is 15 in this case. On the other hand, map width is the number of columns we have, right, horizontally in each row. So we have 7 columns here for each of the 15 rows. Then we have our paths constant, which is the maximum number of paths we want to generate for the whole map. Mind you that this doesn't mean that we have 6 different starting points here at the bottom and we generate 6 fully distinctive paths, because the only constraint we'll have is that at least 2 of those starting points should be unique. So it can be that we have 6 paths configured, but we still have 2 or 3 starting points only, because the different paths can start from the same starting point. The only restriction is that at the end, there must be at least 2 unique starting points. So these last 3 constants are all related to room type distribution at the very end. So when we'll have our remaining rooms, we need to randomly roll for room types. And these random rooms can be either monster rooms, shop rooms, or campfire rooms, and they all have a weight assigned to them. So we have a chance or weight of 10 of spawning monster rooms in this case, 2.5 for shops, and 4 for campfires. Again, you can play around with these values to see what you like for your game. Next up, we'll also need some member variables. First of all, we'll have a random room type weights dictionary, which has the monster, campfire, and shop room type keys, and the values will be those accumulated weights. By now, you might recognize this because it works really similar to what we did with the card rewards and earlier in Season 1 with the enemy actions. So it serves a really similar purpose here too. We'll also have a variable for the total weight, and last but not least, we'll have a map data variable, which is sort of the most important variable in this whole class, and it will be an array of arrays. So what does that mean? Let us go on a little tangent here. So we said that we store this whole map as a grid, right? So what does that actually mean? This grid-like structure we have here with the rows and columns is often referred to as a matrix in computer science terms. So we said that the whole grid or this map data variable will be an array of arrays, right? So we use these brackets to kind of indicate that this is an array. And all arrays have elements, right? So for this array, we'll refer to as the outer array because the elements of this array will be arrays themselves. And what this means is that this outer array here consists of 15 different elements, right? So we can use indices to identify them from 0 to 14, just like we normally do with arrays, right? And I did a reverse numbering here on purpose because we'll start from the bottom when we generate our map. So we have this outer array, which consists of 15 elements that are arrays themselves. And we refer to those 15 arrays as the inner arrays. And the inner arrays always have 7 elements, so we can use indices to identify those elements from 0 to 6. So how do we use this in code? When we have a variable called grid or map data, I use grid here to refer to this whole structure we have. And when we say I take the 5th element from the grid, which has the index of 4, it refers to that whole floor, right? This inner array. But when I say I take the 14th floor's 3rd element, that refers to one specific room, right? Because at first I grab the element with the index of 14 from the outer array, which will be this floor. And since that's an array too, I can sort of use another index to refer to one single room element within that floor. And incidentally, this room will be the boss room always, right? So hopefully this little introduction helps you to wrap your head around using an array of arrays, which are often referred to as matrices in computer science. So just as a quick recap and reminder when we deal with the code next, when we loop through the grid itself or the map data itself, first we loop through all the floors, right? Because we start from the outer array. And we refer to these indices in two different ways. So we either say rows or use a member variable called I, which is a pretty common practice when you deal with matrices. So again, these outer indices from 0 to 14 will be referred to as rows or I, and those inner indices within a floor from 0 to 6 will be referred to as a column or simply just J, which is again, a pretty common variable name when you work with matrices. If you ever feel yourself confused with the loops we have within the code in the next steps, make sure to come back to this part of the video so you can sort of remind yourself and build this mental image of working with a matrix. Cool. Okay, so we can finally start coding the logic for generating the map. And we'll break this down into very distinctive different steps so it's more digestible. And also we can sort of follow the logic of the articles algorithm, which was mentioned earlier. So the main method or the main function of this whole class will be called generateMap. And this returns an array of arrays, which is basically the completed map. And what this means is that this is the function the map scene itself can use to actually display the map in the game. So what do we need to do here? If you remember, the first step was to sort of prepare the initial grid because this array of arrays is completely empty for now. So what we do is we call a method called generateInitialGrid and we assign the result to our map data variable here. Okay, but how does this generate initial grid method works? So what we do is, again, we return an array of arrays, so we can sort of build that 15 by 7 grid. And what we do is we declare a member variable here called result, which will be an array of arrays, and it will be empty by default. Then we create a for loop, which will loop through the numbers of floors we have, right? So we'll have 15 floors here, and we need to generate them one by one. And here, for each floor, we need to build a whole new array, right? Because if you remember, each floor is an array itself, namely an array of rooms next to each other, 7 rooms, right? So we'll call this array adjacent rooms. And here, we also need to start a loop, which will repeat for the number of rooms we have, right? Which is 7. So that's why we loop through the map with constant. And if you remember, I said that for the outer array, we use row or I to refer to that index. And for the inner array, we use column or J to refer to that inner array's index. So this is why we call those loop variables I and J respectively. So in this inner loop, what we do is we create a new room resource and we calculate the offset, right? And we use this placement randomness value because if you remember, we don't want the whole map to look like an Excel spreadsheet. So we use this placement randomness constant to create a vector 2, which we can offset these rooms with. And what roundf here does is it generates a random floating point value between 0 and 1, right? So we can multiply this with our placement randomness to get a vector 2 between 0 and 5 in this case, which is the value of this constant. And then we set a whole bunch of variables or properties of that new room we just created. So how do we calculate the position of the current room in the world of the game? Well, it's pretty simple actually, right? Because we have the constants for the gaps on the x and the y axis. So what we do is we multiply the I and the j indexes with that value and we get the position of that room. One thing we need to make sure of is to actually multiply the y distance by -1 or change the sign of it to be negative, because if you remember in Godot, -y means going upwards, right? And we want floor 0 to be at the bottom and we want the boss room floor 15 at the top. Sort of going to the next floor, we want this to be above the previous room. So here this is why we use a -y. And then when we calculated that vector 2, we had this offset vector to it. We just calculated above with the placement randomness value. Then we set the room's row and column properties to the I and J index we currently have to make sure that we can also store that information in the room resource. And then we set the room resources next room's property to an empty array. Why? Because if you remember, this next room's property will store all the other rooms you can go to from this room. But since we haven't set up any connections yet, we just want to make sure that at least an empty array is there. And here we still have something left to do, because for the boss room, we don't want this y value to be random. We don't want it to be placed randomly. So what we do is we check if the I value we currently have is equal to floors -1, meaning that we're on floor 14, which is the last one, right? If that's the case, we want the y position to be I plus 1 multiplied by the -y distance. So what we do is we override the randomly assigned value. And the question you might ask is, hey Adam, why do we need this I plus 1 here for all of the other rooms? We just use the I index like so. So the reason why I added +1 here is because I sort of wanted to elevate the boss room from the campfire rooms below, right? Adding 1 basically means doubling the distance between them, right? If you think about it, for the campfire, this I will be 13 and the Y position will be 13 times -25. And for this one, it will be I plus 1 and I will be equal to 14, floors -1. So 14 plus 1 is 15. So this will be 15 times -25. And this means that there will be a 50 pixel distance between the campfire rooms and the boss room. And this is useful because if you want the boss room to have a bigger icon, for example, you have the space to do it. Right, but we only need to do this for the boss room. All of the other ones could be placed randomly with that offset to make sure it feels more organic. And then we're ready with the current room basically, and still within the inner for loop, we want to append this room and add it to this adjacent rooms array we have. And what this means is that by repeating this whole process 7 times for each floor, right, we sort of fill this adjacent rooms array up with the 7 rooms we have on the current floor. But we also have this result array declared at the very top of this function because we need to return this whole grid, right? And all the floors will be filled up with 7 rooms. So what we do is in the outer loop, meaning that when we are done with adding all the 7 rooms to the current floor's adjacent room array, we can append this whole array to our result. So let me walk you through this whole method again to see how this looks like. Just as a quick recap here. We have an array of arrays which we call result. We start to iterate through the number of floors we want to do. So whatever is inside this loop, this whole thing will be repeated 15 times, right? So let's imagine we're doing this for the first time. What we do is we create an adjacent rooms array for floor 0, which will contain all the 7 rooms we want to generate for floor 0. We call this array adjacent rooms. And to generate those 7 rooms, we again have to start a loop, which this time will repeat 7 times, because that's what we have for the map width. That's how many rooms we want to have within one floor. So again, the whole thing I selected will be repeated 7 times. And what we do is we create the new room, which is a room resource, and sort of set all the positions, all the indices, and all the properties we need to set. And we sort of handle the boss room differently because we don't want the placement to be that random for the boss room. And finally, when we're done with all these preparation stuff for the current room, we can append it not to the result array yet, but to the adjacent rooms array, because we first have to fill that inner array of 7 rooms. And just when we're done with that, meaning that this loop has repeated 7 times for the current floor, floor 0, then we can append this adjacent rooms array to the result. Because we have filled it with the 7 rooms we need to, and it's a complete floor, we append it to the result, and we go back and repeat this whole process again 14 more times. Hopefully that makes sense. And one final thing that's left to do for this method is to actually return the result array, because if I scroll all the way up, you can see that this method should return an array of arrays, which we assign to this map data variable in the generate map function. So far so good, hopefully. So again, I zoomed out a bit just so you can see this whole method together, right? This is what we do to generate the initial grid. So that's step 1 done in the algorithm. But before we move on to the next step, we might want to test if the generate initial grid method works or not, right? But we have an error message because I said that this generate map method should return an array of arrays, and it doesn't return anything yet because we haven't finished it, right? So what we can do is for now just add a few new lines and say return, and we just return an empty array so that error message should disappear. Mind you that this is really temporary because in the end we really want to return that generated map. So how do we test this? What we can do is we can take this map data now and print it out to the debug window. But in order for the results to be meaningful, what we do first is we loop through all the different floors so we can number them. And how do we do this? Well, we'll just declare an I variable, which will be equal to 0. And then we can loop through all the floors in the map data array, which, if you remember, will be arrays themselves. And within this for loop, what we can do is we can print out something like floor $%s, and this will be which floor we're in, then a semicolon, and then we can show the whole array there. And we need to sort of fill those placeholders in. So for the number, we'll use the I variable, and the whole floor will be use the floor variable, which is the loop variable here. And what we also need to do is make sure to increment this I variable by 1. And this code should be enough to test if this generate initial grid method works or not. But let's not forget to call this method actually in the ready callback. And we can either do this here or do this in the map itself, but it's fine to do it here just for testing purposes. So we'll override the ready callback and call this generate map method. And that should do it. So if we run the map scene and go to the debug window here, we should see all of our floors from 0 to 14. And you can see that all the rooms are using their toString representation, which we provided, with the column value and with the type of room we have in parentheses, which is for all of them will be N. That stands for not assigned because we haven't assigned any different room types yet. And one thing we can do to sort of improve this is to make sure that we don't use a space between the variables, but we use a tab instead. So if we go back to the code and this print message, we can replace this space here with a tab character. And if I run it again, that should give me a more even. Yes, and it does. So if you take a look at this, we made sure that this initial grid assignment works perfectly fine. So now we can move on to the next step. So step 2 will be picking the initial starting points where we generate our paths from. But before we do that, we can get rid of this temporary debug print message we have here by deleting these lines of code. And what we'll do instead is we'll call a method called getRandomStartingPoints, and we'll store the return value of that method in a variable called startingPoints. So let's see how that method looks like. So this getRandomStartingPoints method will return an array of integers. Why? Well, because if you think about it, we want the starting points to be at floor 0 at all times, right? So we don't need to generate a row index because we already know that the index will always be 0, right? So we just need to pick random values from floor 0, which will be a column index, right, for each point. And what we do is we make sure that at least 2 unique points are given as a result. It can be more, but why? How many points we need to generate here? If you remember, we have a constant called paths, which is set to 6. So we'll generate 6 starting points for these 6 paths, but that doesn't mean that we always have 6 unique starting points, right? Because the rule states that these 6 starting points should contain at least 2 different values. That could result that we only have 2 starting points because let's say we rolled column 3 5 times and column 6 1 time, right? That adds together to a total of 6 and it has at least 2 unique starting points. But we could also roll for a third starting point too. So it could mean that the 6 rolls we did between 0 and 6 resulted in 3 different unique numbers. But it could also be 4 different ones, right? And in theory, it could be 6 different starting points, but also there's a really low chance that we roll just one index 6 times, right? So this is why we need to make sure that at least 2 unique starting points are there. First of all, we'll declare 2 variables, one for this array of ints, which will include the final y coordinates, and one called unique points, which we default to 0. So what we do is we include an outer while loop as a safeguard to make sure that we keep repeating generating those 6 numbers until we have at least 2 unique points, because at that point the while loop will break and finish its execution. And what we do when we begin generating those 6 points is we reset the unique points to 0 and also sort of reset the y coordinates result array to an empty array because we haven't generated anything yet. And then what we do is in an inner for loop, which we repeat 6 times, right? Because that's what we have in our paths constant. We roll for a random starting point column index between 0 and map width -1 because the indices go from 0 to 6. Then we check if the y coordinates array already has this starting point or not. And if it doesn't, that means that we find a unique point, so we can increment the unique points variable by 1. And then, regardless if it's a unique path or not, we append the starting point to this y coordinates array, which will have those 6 starting points for the paths. And then finally, when the while loop finishes its execution, it means that we found a configuration of 6 numbers which have at least 2 unique points, so we can return from this function and we'll have all of our starting points in the y coordinates array. And basically that's it for step 2. That's all there is to it, to picking those random starting points, adhering to the rules we just established. But how do we test this? Well, this is just an array of integers, so we can always take a look at what we have when we call this method by going back to this generate map function. And you see we store this array of ints in this variable because we'll use it for the next step. But for now, what we can do is we can just print this starting points array to the console. And if we run the map scene again, you can see that we'll have a configuration of 6 numbers, which always includes at least 2 unique points. In this case, we have 3 different starting points for the 6 paths. 3 of those rows rolled for the last column. 1 of them is starting from the first one, and 2 of them will start from the second column. And if we close this and run it again, we can make sure that it's random. And indeed it is. This time we rolled for 4 different starting points, right? column 0, column 6, column 2 2 times, and column 3 2 times as well. So that's it for step 2. If we close this, we can remove this debug print message before moving on to our next step. And our next step is probably the most interesting one, which is actually generating those paths from the starting points we have. And first of all, let me go through the code we'll have in this generate map method, and then I'll show you the visuals to sort of help you understand what's going on better. So we need a loop through all the starting points, right? And this loop will contain j indices because the starting point array will have column indices, right? Because we already know that these are on floor 0. And we also need to store the current j we have in a different variable, which I'll come back to in a second. And then we can start a sort of inner loop here, which will loop through the i's, so the rows, right? Between 0 and floors -1, because we don't want to go all the way to the boss room because the boss room will be handled differently. So what do we do here? We have a method called setUpConnection, to which we pass the I index we have and the current j index we have. And you can see that this method will also return something because we'll assign it to the new current j. So how does this look like? What does this code really do? So let's say that we have our path and we generated 2 starting points, right? We have these column indices. This one will be at index 2 and this one will be at index 5, right? So what we do is with the outer loop, we loop through all these starting points. But then we have an inner loop. And what that inner loop does is it will build this whole path all the way up to the top of the floors. Because if you take a look at that inner loop, it loops through the i's, meaning the row indices, right? And what this setUpConnection method will do is it will take this current room index we have, which will be 0 and 2 in this case, and it will randomly pick between the 3 different possible connections here, right? So we can go towards the left, we can go directly above, or we can go towards the right. And sort of repeating this process, we can build up this path like this. And with the setUpConnections, we sort of also draw the lines between them. And you can see that these are 2 paths, not just one, but the process remains the same. So why do we need that current j variable? Why do we need to return anything from this setUpConnection function? And the reason is pretty simple, right? So we start from this one, 0 and 2. And then what we do is we chose this room to be the next one from that starting point. And that means that we set up this connection between the 2 rooms and the inner loop can go to the next iteration, right? So the I will be 1 in this case and the j will be 1, 2. And this is super important that we update the j variable because for this one, this room, the second one we have here, the 3 possible next rooms will be much different, right? Because it can go to the left again, go directly above and go to the right. But you can see that those j indices will be different, right? Because this is 0, this is 1, and this is 2. And for the first room we had here, the possible j indices were 1, 2, and 3. So if we didn't update the j, the column index accordingly, we would pick between these 3 possible next rooms, which is incorrect, right? So whenever we set this connection and move on to the next one by incrementing this I or row index in the inner for loop, we also need to make sure that we have an updated j index as well to know where the room exactly is where we go from. I hope that makes sense. And we repeat the same process till we filled up the whole stuff all the way up to the boss room. And when we're finished, we can move on to the next starting point and literally do the same, right? Generate the path and set up all those connections between them. So this is what this algorithm does, but we are still far from finished, right? Because we don't have that setUpConnection method yet. So let's see how that works. Right, so what do we need to do with this setUpConnection method? First of all, you'll see that we have 2 parameters, a row and a column index named I and j. And we also need to return an integer from this method because we have to update that column index for the next room, just like we discussed. So first of all, we'll define a variable for the next room candidate, which will be a room resource. And we also need to grab the current room we have by using that I and j parameters to get the current room from the map data array. We'll also use the s keyword to cast it to a room resource, so we have IntelliSense in this method. And then what we do is we create a while loop here. So how does this while loop works? Well, we need safeguards here too. So we have to pick a new next room if we either don't have one, meaning that we don't have a next room because the next room is null, or we also have to pick a new candidate for the next room if the one we picked would cross an existing path. And that's something we need to discuss further in a second. But let's see what we do in that loop first. So when we need to generate or pick a new next room for the current room, what we do is we pick a new random j, meaning that we grab a new column index. And most of the time, this new column index means choosing one from 3 possibilities, but not always. So what we do is we subtract 1 from the j and add 1 to the j as well. And this is the range we want to get this new index from, but we actually have to clamp it between 0 and map width -1. Why? Well, because if the current room we're working with is at either side of the grid, meaning that it's in column 0 or column 6, we need to make sure that we don't generate an index which doesn't exist in the grid, right? Because if we're at column 0, j -1 would be -1 or -1, and we don't want to use a negative index. In a similar fashion, if the column we're currently in with that room is column 6, j +1 would be 7, and we don't have an 8th column in our grid, so that would result in a runtime error. So we need to make sure that we clamp this variable. So sometimes it's only just an option between 2 different possibilities, but most of the time it's a pick between 3 different column indices. And that's the hard part really, because the j is the only one that's random, because we already know the row index, right? So we know that the next room will be 1 level above the current one, and the j can be that random j or column index which we just picked. And that's all we need to do in the while loop itself. And after the loop exits, we can say that the next room we found for this current room is a viable one. Why? Well, because this loop only breaks out if we have a next room, meaning it's not null, and it wouldn't cross an existing path, right? Because if either of these are true, we sort of repeat this process until we find a viable one. So if we do have a next room and it doesn't cross any of the existing paths, it means that we have a viable candidate, and we can take the current room's next rooms array and append this next room to it. Because if you remember, in the room resource, we have this next room, which is an array of rooms containing all the information of which rooms we can go to from the current room. And that's all we really need to do, but let's not forget to return that new column index we picked, and here we can use the next room's column property, or we can use the random j. It doesn't really matter because they refer to the same index. Right. That's it for the setup connection function, but we still have this crossing existing path business, which we haven't really talked about yet. So let's assume that we have these paths here, right? And assume that the blue ones were generated first. So when we actually pick the next room for this red node right here, we need to make sure that setting up a connection doesn't result in crossing an existing path. So what does this mean? It means that we take this node we have, and we have the ij, or the row and the column indices for that one, and we need to take a look at both of its neighbors, right? So with the right neighbor, we doesn't really have anything to do because that room isn't assigned. It's not used, right? So there's no paths generated from that node, so we can't cross anything here. But we also need to take a look at the left neighbor, right? Which is that node right here. And that one actually has 2 rooms in its next rooms array, one pointing towards the left and one pointing towards the right. So here, this line or this next room would actually violate that rule, right? Because you can see that this arrow here indicates that we go from this left neighbor to this orange room here. And if we look at our original room, we have these 3 candidates, right? And this one, which goes directly above, is absolutely fine because if you go above, you can't cross any paths. And this one would be fine too because the right neighbor is unoccupied, right? So this line couldn't exist because this node isn't used at all. So this one would be fine too. But you can see the crossing pattern here, right? So you can see that we have a left neighbor, and that left neighbor has a next room which goes to the right, and we want to go to the left. That's violating the rule. So let's see another example and assume that the orange paths were generated first. Then let's take a look at this blue node here to see if the next room candidates we have are actually viable or not. So this time let's start with the left neighbor. The left neighbor exists and it only has one next room which is directly above it. This means that this line here doesn't violate any rules, right? I can go towards the left here, it doesn't cross any paths because this left neighbor doesn't have a path that goes to the right. So there's no crossing here. However, if we take a look at the right neighbor, it has two next rooms, right? One directly above and one which goes to the left. And this means that we have a crossing path here as well because we want to go to the right, but we have a right neighbor which is going to the left. And you can see that there's a crossing pattern here as well. So these are the two possible ways to violate this rule. I hope that makes sense. But let's see how we can do that in code. First of all, we'll have two member variables for the left and right neighbors respectively. Also, we need to make sure that we pass the original rooms I and j indices or row and column indices and the room candidate which we want to set up the connection with. And this method returns Boolean indicating if we would cross an existing path or not. So again, if we're examining this node here, the I and j will be the coordinates of this one, and the room parameter will be the candidate, right? So this one, for example. After declaring the variables for our neighbors, we actually need to see if we have them or not. Why? Well, because if the j is 0, that means that we're at the left edge of the grid and we don't have a left neighbor, right? But if it's bigger than 0, then we do have a left neighbor, which is within the same floor, but 1 unit to the left. So I and j minus 1 will be the coordinates of the left neighbor. For the right neighbor, we kind of do the same, but on the other edge of the grid. So if j is equal to map with minus 1, that means that it's in column 6, which is the last one, and it doesn't have a right neighbor. But if the j is smaller than that, then it does have a right neighbor. And we can similarly get this neighbor by referring to the same I or row index and incrementing the j index by 1. Then after grabbing the neighbor, we need to take care of those two cases we were talking about in the visuals. So we can't cross in the right direction if our right neighbor is going to the left. And if we first of all check if we do have a right neighbor, because if we don't have a right neighbor, we don't really care, right? There's nothing to examine. And to make sure that there is something to look out for, if we do have a right neighbor, we need to check that the room candidate, which we want to go towards, has a bigger column index than the parent's j index, right? Because that means that we want to establish a connection which goes from the parent room towards the right direction. And if both of those conditions are met, we need to check if there's a crossing or not. So what we do is we iterate through all the connections in the right neighbor and check if there's a connection to room which has a smaller column index than the room we want to go to. And if that happens anywhere, that means we crossed a path. And in a very similar fashion, we kind of want to do the same thing for the left neighbor. So first of all, we'll check if the left neighbor exists and there's something to examine, which in this case means that the room we want to go towards is to the left from the parent room. And if that happens, we want to iterate through all the connections of our left neighbor. And if there's a connection that goes from the left neighbor and has a bigger column index, meaning it goes to the right, in comparison with the room we want to go to, then we found the cross again and we need to return true because that means that we violated the rule. And if neither of those happen, that means that the candidate we have is perfectly fine because there's no crossing violation, so we can return false from this function. Phew, that was a big one. But that's really the essence of this whole algorithm. Because with this one ready to go, we're basically done with the map generation. All that's left to do is actually assigning the room types based on the weights, which is not that complicated compared to this one. So let's not forget to save this with Ctrl S and see how we can test this out. And again, just before testing this, I wanted to show you this whole method zoomed out so you can see it as a big picture. So this is what we use to check if a next room candidate or a connection candidate would cross an existing path or not. And where do we use this? Just to sort of reiterate those points to make sure that you can understand what's going on. We had a method called setUpConnection, which we just did earlier. And in this method, when we take a room and we want to set up a connection, we need to continue to pick a new candidate for that connection until we make sure that it wouldn't cross an existing path. So this is the use case for this would cross existing path Boolean method. Cool. So to test this out, we can sort of do a similar for loop which we had before. And what we do here is we say for floor in map data, we can print out the current floor we're in. And to do so, we need to make sure that we declare an I variable again, which I forgot. So we can declare this as 0. And what we do here is we only want to display the rooms which have connections, right? And to do so, we'll have to iterate through all the rooms as well. And to do so, we would either need to iterate through all of the rooms, or we can do sort of a filtering here. And we can say something like we create a variable called used rooms. And this one will be the floor, which is an array. And I'll use an anonymous function here. So we can grab the room and return a Boolean variable for filtering, saying that this room has next rooms in it. Basically, that the next room array's size is greater than 0 because we only want to display those rooms. And what we can do is we can print that used rooms array, and we can also actually increment the I variable. So with this piece of test code or debugging code here, we could see if the connections are working or not. So if we run this again, cool, we have something, right? So if we scroll all the way up, we have floor 0, saying that we picked 1, 4, 5, and 6 as starting points. And you can see that in floor 2, we have a connection to column 2, 4, 5, and 6. In floor 3, we don't have 4 points anymore, we only have 3. So we can see that sort of the connection is established between them. It's kind of hard to actually debug this without displaying the connections or writing out the connections, but we can use one little trick here. And that is to make sure that these column indices don't change more than one from one floor to another, right? Because we know that the candidates must be directly above, one to the left or one to the right. And it seems like it's working, right? Because we have 1 here and 2 here, 2 here and 3 here, 4 and 4. So this is a directly above connection. We have 5 and 6. So we can kind of see that the system is working because we don't have jumps between them and we also don't have empty floors. So everything looks fine so far. And one final thing to do with this map generator is to start assigning the room types. And it's partly based on rules, partly based on random generation. So that's a fun little thing to tackle last. So let's start changing those not assigned room types to actually something meaningful. And in the generate map, we don't really have to change much. We can also leave this debugging code here intact because we can use kind of the same one to test the code we do now. But what we do before it is we'll call 3 new methods we have to implement. One is called setup boss room, which does something exactly like the name would suggest. And then we set up the room weights and finally set up the room types themselves. Also, while we're here, we can change this empty return because at the very end, when we're finished with everything, we want to return the map data variable, which will have our complete fully generated map. Right, so we're basically finished with the generate map method, which is the backbone of this whole thing, the orchestrator. We just need to finally implement these 3 methods and we're finished. So let's start with this setup boss room method. This is pretty straightforward, probably the easiest one so far. What we do is we grab the middle index of the whole map, which is basically the map width multiplied by 0.5 and also floored to an integer to make sure that it's actually a valid index. If you think about it, for example, here we have a map width of 7. If we multiply it by 0.5, that's 3.5, and we have to floor this to make sure that we have an integer variable, and flooring this will result in 3, which is a valid index, and we call this the middle. Cool. So we have the column index for the boss room. Then we actually grab that boss room and we already know the row index, right? Because the boss room will always be the last one. In this case, we have 15 floors. So the index will be 14. And in terms of the column index, we just calculated it with this middle variable. So we can get the boss room from the map data grid and cast it to a room resource with the as keyword. Then we need to make sure that we connect all the rooms below the boss room to the boss room, right? So we need to loop through the column indices, the J's. Then we need to make sure that we grab all the rooms which are directly below the boss room, meaning that they are in floor 13 in this case. And this is why we iterate through all the column indices to make sure that all rooms that we are using will be handled. And what we do with this current room, we check if it has any connections generated or not. Because if it does, it means that it's part of an existing path And we need to change those connections because we need to make sure that all the campfire rooms below the boss will connect to the boss, right? So they can't connect to anything else on the last floor because the only thing we want in the last floor is the boss itself. So what we do is we create a new empty array for that room's next room's property and we append the boss room to it to establish that this is the one and only connection from that campfire to the boss. And finally, when we're done with setting up all the rooms below the boss room, we can set the boss room's type itself to be equal to room.type.boss. And that's all there is to it. We're done with this one. And setting up the random room weights for the different kind of rooms isn't that difficult either. We just basically populate the dictionary just like we did with the card rewards and with the enemy actions. So what we do is for the monster, which is the first one in the dictionary, we just take the value from the constant because this will be equal to the accumulated value as well. For the campfire, however, we need to add those two constants together because the accumulated weight will be the monster rooms and the campfire rooms added together. And for the shop, we add together all three of those constants. And for the total weight itself, it will be equal to the shops, right? So we can just reference that from the dictionary, which we just assigned directly above it. And that's it for assigning the random weights. It's not that complicated. And our final method is all about setting up the room types. And this one will be a bit longer, but not the method itself. We just need to kind of implement some supportive methods, as you'll see in a second. So here what we do is we adhere to some rules first. So what's the first kind of thing we can apply? Well, we know that the first floor will always have battles, right? So what we can do is we can iterate through all the room in the first element of the map data array, which will be the first floor. And what we do is we check if the current room is used or not. How do we determine this? Well, if it has next rooms in the next rooms array, it means that it has a path, right? So we basically check if that next room's array is empty or not. Because if it's not empty, it means that we use that specific room. And if we do, we can set the room's type to room.type.monster. Then another rule we need to apply is that the 9th floor is always a treasure room. So what we do again is kind of the same thing. We iterate through all the rooms in floor 8 and we check if the room is being used or not. And if it's being used, that means we can set the room's type to room.type.treasure. And one last similar rule we need to apply is that the last floor before the boss is always a campfire. So we can iterate through all the rooms in the 14th floor. We check if we use that room or not. And if we do, we'll set the type to campfire. Simple as that. Here I also want to point out that instead of using these setting constants or literals like 8 and 13, you could do something like floors -2 and also floors divided by 2 and convert it to an integer or floor it like we did in the boss setup. But here I just opted for a quick and dirty solution because honestly it doesn't really change much, but admittedly the code could be a bit cleaner if we reference that constant instead of using these magic numbers here, but it doesn't really matter. It only matters if you want to experiment with different floor values, especially if you use a smaller value. You need to be aware that you might need to change this, otherwise you get an error message. Here I just use the magic values because it's easier, but you do you. And for the rest of the rooms, we want to do something different, right? So we iterate through all the floors and all the rooms we have and grab all the connections going from the room where we're currently in. And we do a safety check here because we only want to change rooms which are in a path, but they are not assigned to any type yet, right? Otherwise, we would change the campfires, the treasures, and the battle rooms, which we already set up before. And if we have a room which is in the path and is not set yet, then we set the room randomly, which is a new method we need to implement. So how do we set a room randomly? First of all, again, we need to adhere to some rules. These rules are the following. The first rule is that we can have campfires below floor 4. The second rule is that we can have consecutive campfires, meaning that a campfire room is followed by another campfire room. The same applies to shops, and we also can have campfires on floor 13 because that would result in consecutive campfires regardless. Why? Well, because we have that rule that below the boss room, we'll have campfires no matter what, right? So this means that we can't have campfires below the boss's campfires. I hope that makes sense. So what we do is we create 4 flags and set them to true, saying that all of those are violated by default. Then we'll also have a variable for the type candidate, which we roll for. And again, we create a while loop, which is sort of like a safeguard, saying that we keep rolling for a type candidate as long as either of those rules is violated. Because if any of those rules are violated, it means that we rolled for a type which can't be assigned to that room. So we need to roll again. And when we finally roll something that's not violating any of the rules, this while loop will break. So what we do is we first of all grab a type candidate, which will use this method called getRandomRoomTypeByWeight, which we not implemented yet. Then we set a bunch of booleans checking if that type candidate is a campfire or is it a shop. And we also have 2 different flags here. One is called hasCampfireParent and one is called hasShopParent. And for this one, we actually need to implement yet another method called roomHasParentOfType, which we can use to check the parents of that specific room. And when we have all of those variables ready, all we need to do is really set these flags, update them, right? So campfire below 4 is only true if the room candidate is a campfire and that room's row index is less than 3. For it to be a consecutive campfire, it needs to be a campfire candidate and it needs to have a campfire parent. For a consecutive shop, it needs to be a shop candidate and it needs to have a shop parent as well. And for the campfire on 13 to be violated, the type candidate needs to be campfire and the row index needs to be equal to 12. And you can see that if you're not violating those rules, then these flags will become false, right? All of them. And when all of them are false, this while loop will break out, meaning that we have a type candidate which will finally fit our purposes. And if that's the case, all we need to do is update that room's type to this new type candidate. And basically we're done. So this is how we can set a room randomly, but we still need to implement those 2 new methods. So how can we get the parents for a given room? Well, it's easy, right? If I take this room here, you can see that I have 3 parent candidates, 1 to the left, 1 directly below, and 1 to the right. And I need to make sure that I grab these parents here and check if they have connection to me or not, right? This one to the left has a connection to me, so it's a parent. This one has a connection to me, so it's a parent. This one doesn't have a connection to me, so it's not my parent, right? So these 2 are the parents of this room. Well, it's not always that easy, but that's the main idea. What are the edge cases here? Well, if we are on floor 0, these starting points have no parents, right? So we can't check for parents on the first floor. Also, we have some rooms on either side of the grid, right? So at the leftmost side, those rooms can't have left parents by any means. And the same applies to the rightmost side of the grid. So in column 6, doesn't matter what connections these rooms have, they can't have parents to the right. So we need to keep this in mind when we create this method. So how do we check if a specific room has a parent of type or not? The first thing we need to do is to actually get all the valid parents of that given room. So we declare an array of rooms, which we call parents, and it's empty by default. Then we need to grab the 3 possible parents, right? So for the left parent, we need a safeguard saying that the room's column should be greater than 0 because if you remember, if we're on the leftmost side, we can't have a parent, right? And also the room's row index should be greater than 0 because rooms at floor 0 can't have any parents. But if we're not at the leftmost side and we're not on floor 0, it means we do have a parent candidate. And we can get that as a room by referencing the map data's row -1 and the column -1 indices. And to check if that parent candidate is actually a parent or not, what we need to do is check if the parent candidate's next rooms array has the current room we're in, right? And if it does, it means that it is a parent because it has a connection to me. So we can append this parent candidate to the parents array. And we virtually do the same with the directly below parent and the right parent. So for the parent below, the only safeguard or safety check we need is if we're not on floor 0, then we can grab that parent candidate as a room variable and see if it's actually a parent or not. And if it is, we can append it to the parents array. And for the right parent, again, we do the safety check to make sure we're not at the rightmost column and we're not on floor 0. Then we reference the parent candidate with the correct indices. And if it is a parent, we append it to the parents array. Whew, so that was a lot of work just to get the parents, but once we have the parents, what we're actually doing is pretty simple. We just need to iterate through all the parents and check if the parent type is matching to the type we want to perform this check for, right? So if I'm searching for campfires in the parents, then I need to see if the parent's type is equal to campfire. And if it is, that means that we have a parent of that type, so we can return true. But if we iterated through all the parents and we haven't found a match, it means that there's no parent with that specific type, so we can return false. Again, here's the whole method as a whole, so you can see the big picture better. But basically what we do is we sort of divide it into two different parts. This part, which I highlighted here, is just responsible for grabbing all the valid parents of a given room. And this tiny little second part here is actually what we want to do here, which is checking if any of the parents match that specific type we're looking for. And we either return the true value or false if there are no parents matching that type. And the final thing that's left to do regarding map generation is to provide the method to get a random room type based on the weight system we have set up. And thankfully, this is a pretty simple method here. What we do first is we roll for a float value between 0 and the total weight we have. And just like we usually did with these weight-based random rolling systems, we iterate through the keys of the dictionary and see if we have a greater accumulated weight value than the roll we have. And if we do, we can return the type, which means we rolled for that one. But in order to provide a return to all the code paths, we can just by default return the monster room type if for any reason we haven't rolled for anything valid, but that should never happen. And that's it. That's the map generator, which is the longest script or class in the whole project we have in season 2. So great job if you were able to follow so far. And now comes the fun part, when we actually make this alive by creating the visuals, interactivity, and all that good stuff. Hopefully it wasn't a torture and you learned something. Let me know in the comments if I can do anything to make this clearer. So save this with Ctrl S, and let's not forget to test it. But if we go back to our generate map method, if you remember, I said that we can reuse this same debugging code to see what we have here. So why don't we just do that and run this map scene again? And indeed, we no longer see just ends, meaning that it's not assigned, right? So let's test our rules if they're working or not. On the first floor, we only have AMS, which stands for monster, and that's perfectly fine because on the first floor, we can only have monster type rooms. Let's see floor 8, which should be all treasure rooms, and it is. And floor 13 should be all campfires before the big boss. And indeed, they are campfires. And you can see that we have no campfires before them, so it's adhering to the rule that there's no consecutive campfires. And you can see that the most rooms are monster rooms, which is perfectly fine because they have a much bigger weight than all the other ones. We have some shops sprinkled in there and also some campfires along the way. Cool. So basically that's it for the map generation. And we can move on to actually hooking this up with the map and creating the visuals for the map, which will be a much needed break after all this code heavy stuff, right? If you like my content, please consider checking out my Ko-fi page where you can donate one time or become a member and get early access to all my content and videos. So with all our map generation stuff finished, we can actually start creating the visual representation of this map structure we can generate. And before we do that, we can actually get rid of this debugging code we have here because we already tested if it works or not. So we can just delete this part of the code. And this is what our final generate map method looks like. And also, if we scroll up a bit in the ready callback, we call this generate map method to make sure it's called. And we don't need this either because we'll call this method from the map itself, not the map generator. So we can delete this whole ready callback we have here. So there's no extra code remaining, and we can save the map generator by pressing Ctrl S. And we can create the map room scene first, which is sort of a visual representation of the room resource we have. And to do so, let's go back to 2D view. And we'll create a new scene by clicking on this plus sign here. And this time as a root node, we'll use another node and search for area 2D, because we need to be able to interact with this MapRoom object, but we also kind of need to position it in a 2D world, not in a UI space like control nodes. So this is why I opted for area 2D here. We can double click and rename this to MapRoom. And we can also add a couple children nodes to this MapRoom. First of all, click on the plus sign or press Ctrl A, and we'll add a node 2D node first, which will store all the visuals we have for this MapRoom. So double click, rename this to visuals. And under this visuals node here, we'll add 2 new children. So click on the plus sign again or press Ctrl A, search for line 2D and select the visuals again and click on the plus sign again. And this time add a sprite 2D child. We still have this warning message here with the MapRoom because it doesn't have a collision shape set up yet. So click on the MapRoom again, the root node, click on the plus sign and search for collision shape 2D. And before we set up any of those nodes we added, we need one final node, which is an animation player. So we again select the root node, click on the plus sign and search for animation player. Right. So these are all the nodes we need, and we can zoom in a bit just to see what's going on better and configure them one by one. First of all, for the MapRoom, the area itself, we can set the collision layers properly. So if we go under collision, we don't need to set any masks because we don't look for any collisions with this layer, but we can set it to a different layer from all the ones we currently have. And layer 1 is unoccupied. And what we can do is we can also rename this by right-clicking on it and call this map rooms or something like that to make sure that all our layers are tidy and separated. Right, that's all the setup we need for the area itself. Now let's move on to the sprite 2D so we can see actually what we're doing here. And for the texture, we can load something from the art folder. For the battles, I use this little knife icon here. So I double click on it and you can see that we have our image. Cool. Let's also add the collision shape because we still have this warning message here that there's no collision shape attached to this node. So click on this empty here and I'll use a circle shape 2D. And what we use this collision shape for is basically the area which you can click on for this node. And by default, if you click on this circle shape 2D, it has a radius of 10. And I think that's perfectly fine. It's a big enough circle. We can just simply click on it. If you want to, you can make it bigger or smaller to your liking, but I think that 10 pixels is perfectly fine. Right, before doing the animations, there's one last thing to do, and it's setting this line 2D node, which we'll use for highlighting selected map rooms. And while we're doing this, we can hide the collision shape so we can see our line 2D better. And for making this or creating this line 2D, I'll turn on the grid so we can have something to rely on when we add the points. But this grid is kind of big. So if we go to these 3 dots here called snapping options, we can configure the snap and set the grid step from 8 pixels to something like 2 maybe and zoom in. So we can create this little pentagon shape around it a bit easier. For the line 2D itself, I don't use a width curve here. I'll just simply use a width of 2 pixels and you can set the color to whatever you like. I'll just use a gray color here like so. And what we do is we select this create points button here up at the top and we can sort of start adding points to this little outline we want to have, and you can do whatever shape you like. So something like this looks fine, even though it's not a pentagon as I said, but doesn't really matter, just use a shape you like. And what we can do is we can set this closed property to on, and what it does is it connects the first and the last points together, which is perfectly fine. I think that looks okay. If you want to move around the points or experiment a bit, what you can do is you can select this edit points button instead of the add points, and you can drag those little points around. Maybe we can do something like this to make sure it encapsulates the whole icon a bit better. Yeah, and that looks perfectly okay to me. Nice. So we have our line 2D ready to go. And all that's left to do here is to actually create some animations to make it a bit more interesting. And before we do that, let's not forget to turn this collision shape back on and click on the animation player to create those animations. And we'll basically have 2 animations and kind of an extra one. So one animation will be played when a map room is highlighted, which means that if you can choose between different rooms in the map, all of the available rooms which you can click on will sort of pulsate to signal to the player that they can click on it. So go to this animation button here, click on new, and we'll call this animation highlight. Add this new animation here. Click on this button, this arrow button, to turn on animation looping because we want this animation to loop. And you can see that we have all these key icons here, so we can animate all the properties we have. And we want to actually animate the visuals here. So click on the visuals, expand the transform group, and we want to animate the whole scale of this map room. So click on the scale, and we have this little window here that we create a new track for the property scale and then insert the key. And what we can do is we can create a reset track. And we actually want to do that. So let's make sure that this is checked and press create. And what this does is it creates another animation with which you can always reset to the default values in the editor. But that's also a valid animation on its own, which we can use in our code if we want to. So in our highlight animation, we have one keyframe here where the scale is 1 and 1, which is perfectly fine. And we can use the mouse to sort of scroll between the different durations or points we have in this animation. And at halfway through, at 0.5 seconds, we want to create another keyframe. And if you want to see what's going on a bit better, you can hold Ctrl and scroll with the mouse wheel to zoom in on the timeline. And we want another keyframe here. So if we click on the visuals node again, we can set the scale to something like 1.25 maybe. And you can see everything gets bigger because both the line and the sprite nodes are children of this visuals node. And we can click on this key again, and this will create a keyframe at the current cursor position, which is exactly what we want because we have this animation going already. And if we play the animation from the beginning, it should loop and highlight this map room here. It looks perfectly fine, but by default, we use no easing and we use a linear interpolation between the keyframes. So if you want to make it a bit more interesting, you can experiment with this by selecting this little yellow icon here and change it to cubic, for example, and you can see if that looks better. I kind of like cubic interpolation for this, and I don't think it needs additional easing, but if you want to, you can change the easing too by selecting a keyframe, and you can see that we have this easing curve here. And what you can do is you can right click and you can use some built-in easings if you want to. We can use ease in out, for example, and then this curve looks like this. And if we play the animation now, then it should have an easing to it. So it looks more snappy in this case, I think. You can use whatever you like. I kind of like the linear easing on it with this cubic interpolation, so I'll leave it at that. And because the looping is enabled, that's all we need for our highlight animation. We can pause this, but we also need an animation to play when we click on an available map room and we want to play a select animation. This pentagon or this hexagon in this case, or this highlight area around the icon shouldn't be displayed by default, only when we select one. So we'll add a new animation, click on this animation button again, click on new, and this time we'll call this select. And you can see that a new animation gets added here. And the select animation can be a bit shorter. So this is the text box where we can set the length of the animation. So from 1 second, we can change it to something like 0.6 maybe. And what we want to do is to select the line 2D node this time. And under canvas item and visibility, we have modulation. So we can set it to fully transparent by default by clicking on this white rectangle here and setting the alpha all the way to 0. And you can see that we no longer see our line. And if we click on this key, we can add it as a first frame. And also add it to this reset animation to make sure that by default, it won't be visible. And what we do is, let's say in 0.3 seconds, we change this modulation from fully transparent to fully opaque. So again, click on this rectangle here, and this time crank it all the way up to maximum and add another keyframe here. And you can see that if I start to scroll through this animation, it will sort of fade in from fully transparent to fully opaque. Again, you can play with the easings and the interpolation. I'll use cubic for this one too. And if we select the map room so we can see what's going on better and maybe hide the collision shape, we can see what this animation is going to look like by playing this. Yeah, I kind of like that. And you can see that it's not looping because we haven't clicked on this button, which is perfectly fine because we don't want this to loop. We want it to stay selected when we play this animation. Cool. We'll also call a function here later on, but since we haven't added any scripts to this scene yet, that's all we need to do for now. And one thing I wanted to show you is this reset animation we can create. Because see, if we play this animation and go to the editor and start to change up things, you can see that this line 2D stays visible, right? Because we play this animation. But if you click on this reset animation, then it will reset all the variables, all the properties be sort of overwritten. The scale of the visuals node and the modulate property of the line 2D, so we can always go back to this animation to reset it in the editor, which is a pretty cool feature. So with all the setup stuff done, we can actually create the code for this MapRoom scene. But before we do that, let's not forget to save this because this is still unsaved, right? So press Ctrl S to save the scene, go to scenes. And I think we can save this in the map folder because we won't be reusing it elsewhere. So under map, we can save it as maproom.tscn. Cool. Now we can go to the coding part, but this will be much easier compared to the map generation itself. We can select the root node, the MapRoom node, click on the attach script button. MapRoom GD is perfectly fine, but we can change this template from node default to object empty so we don't have auto-generated code. Click on create. And before we actually start the coding part, we need to connect one signal in order to avoid typos. I'll show it to you here. So click on this MapRoom node again, go to the node tab, make sure that signals is selected. And we want to connect to the input event signal so we can register clicks on a MapRoom. Double click this. On input event is perfectly fine for the method name and click on connect. And you can see that we have our input event method generated for us. Perfect. Right, so how do we create the code for this? First of all, we'll provide a custom class name called MapRoom. Then we'll have a signal called selected with the room as a parameter so the other systems can know which room was clicked on. Then we'll have a constant dictionary called icons where the keys are room types, so these not assigned, monster, treasure, and so on. And we have an array assigned to all of those types with two different values in them. The first one is an icon texture itself, which is preloaded. And the second one is the scale with which we want to use that icon. That's useful because, for example, for the boss rooms, you might want to use a bigger icon to sort of emphasize the importance of that little room. And these icons are all loaded from the art folder. Then we have three already variable references to the sprite 2D, the line 2D, and the animation player nodes. And we'll also have two member variables. One is called available, which is a flag. And we'll also have a member variable called room, where we can store that room data container, which belongs to this MapRoom visual representation. Both of those member variables have their own setter functions. So let's see for the available property first. So what we do is we set this available member variable to the new value we have. Then if that new value is true, we can start playing the highlight animation on loop, right? Because being available means you can click on that specific map room. But if the available is set to false, we need to check if the room was selected previously or not. Why? Because if we selected a room previously, it means that we're sort of done with that room and we moved upwards in the hierarchy, right? And in this case, we don't want to play the reset animation if the room was previously selected, because then the outline, the line 2D, would disappear again, right? It would set the modulate to fully transparent, and we don't want that. But for rooms that are not available anymore and were not selected before, we want to play the reset animation. Why? Well, because on floor 0, when we start to run the game, all of those available starting points will start playing their highlight animations, right? But if we click on one, it means that all of the other ones adjacent to those, the other starting points, should not play that highlight animation anymore because we won't be able to click on them. So this is the case when we play the reset animation to make sure that the visual nodes scale reset to the default value. As for setting the room resource itself, what we do first is we set the new data to the room property, and then we set the position of that 2D MapRoom node in the world to the position we stored in the room resource. So this is what I meant by 2D world position in the architecture overview. And for the line 2D, to make it a bit more interesting, so not all the rooms have the same sort of outline around them, we assign a random degree of rotation to this line 2D node, and we set the sprite 2D's texture to the icon based on the room type, and set the scale from this icons dictionary too based on the room type again. Because if you remember, in this icons constant dictionary, all of the values assigned to the keys are arrays of 2, where the first element is a texture, which we can set as the sprite 2D's textures property, and the second element is a scale, which again we can set as the scale property for the sprite 2D node itself. And that's all for the setter function. We'll also provide a utility function which we won't be using here, but we'll expose so we can use it from other classes later on, namely the map. And this method is called showSelected, which will set the line 2D's modulated property to a fully opaque white to make sure that we can see that this was selected before. And we also have this onInput event callback, which we connected earlier. And what we want to do in the case of input event is provide a safety check first. So if either this MapRoom is not available or the input event we registered is not a mouse click, then we can return from this function immediately, because we only want to deal with input events in the case of available MapRooms which register a mouse left click, right? And if we did register a left click for an available MapRoom, what we do is we set the room's selected property to true, and also play the animation player's select animation. And what we also want to do is after this select animation has finished, we want to emit the selected signal, but only after it. Why? Why don't we just write this selected.emit in line 50 directly below the animation player.play? Well, because if we emit the signal immediately, then the player can't see the animation, right? Because we would immediately transition into a campfire scene or a battle scene. So we want this animation to finish playing, and only after it did, then emit the signal. So we can make this switch not immediate, but 0.6 seconds, because that's how long our animation is. So what we do is we provide a callback function here, which only does one thing, which is actually emitting this signal. And we could certainly do it here by using await to wait for the animation player to finish. But there's also another way to do it, which is to actually create a keyframe for calling this method in the animation player itself. And it's a really handy method, but it makes it a bit harder to keep track of the flow of the logic, and this is why I wrote this comment here. So when you read through the code, you can see that, okay, we have this function here which is called nowhere seemingly, but you can see that this animation player node will call this, right? Because you have this little reminder comment here. So let's actually call this. But first, save the script by pressing Ctrl S. And how we can do this callback in the animation itself is by going back to 2D view, selecting the animation player, switch to the select animation, and we can add a new track here with this plus button. And we'll say that we'll use a call method track here, and you need to select the node which you want to call a function on. And since we want to call the MapRoom's callback method, we select the MapRoom here, click OK. And if you use the mouse to scroll all the way to the end of the animation at 0.6, we can right-click this point in the timeline and say Insert Key. And you can see that we have this pop-up window where all the available methods to call will be listed here. And from the script methods, we want to call this onMapRoomSelected we just created. Click on Open. And you can see that this little icon appears here and shows us that at 0.6 we'll call this onMapRoomSelected method. Cool. So that's all we need for the MapRoom, and we can save this with Ctrl S, but we need to test it somehow, right? So if we go back to the script, we can add some debugging code in the ready callback. So what I do here is create a new test room, set the type to campfire, and set the position to 100 and 100 to make sure that we can see it, and set the room property of this map room to this test room we have. After that, we'll create a timer in the scene tree for 3 seconds and set the map room's available property to true so we can test what clicking on it does. And that's all the code we need to test this. So we can run this currently open scene by clicking on this icon here, and you can see that we have this heart icon, and after 3 seconds it starts pulsating because we set its available property to true. And when it's available, I can click on it, this little selection animation plays, and it no longer pulsates. And we emit the signal, but we don't do anything with it yet. But this looks perfectly fine, but if we run it again, I can try clicking on it in the first 3 seconds, and I'm clicking like crazy, but nothing happens because when it's not available, you won't be able to click on it. Perfect. That's all for the MapRoom for now. But before we move on to hooking this actually up in the map scene, let's not forget to delete this debugging code. We just use this to test if it works or not. And we can save this with Ctrl S before moving on to the next part. One last piece of this visual puzzle before we can hook all the stuff up is the connecting lines between the different map rooms. And we'll create this as a unique scene itself too. So what we do is we go back to 2D view, click on the plus sign to create a new scene, and we'll use another node as a root node, and this time we'll use Align 2D as a root. Double click and rename this to MapLine, and press Ctrl S to save this in the same folder under Scenes and Map, and we can call this MapLine. And this is super easy to set up. We want a repeating texture to show this little dotted line, right? And I prepared the texture for you in the art folder. So let's zoom in a bit first. And we can turn this grid off for now, so it's easier to see what we're doing here. And what we need is we need to expand our fill under the line 2D's inspector variables and use a texture here. So click on texture, load. From the art folder, we have a line.png. Then we need to set the texture mode to tile, and also under canvas item and texture, we need to set the repeat property, which is disabled by default, to enabled instead. And then with these three little changes, again, the texture mode, and the repeat property of the canvas item texture, we can start testing this by putting down a few points here. And you can see that it has this repeating line texture, but it's kind of hard to see how this looks like in game. So if we run this scene to test it, you can see that this is how it looks like, very pixelated in the game. And this is exactly the solution I used in the project. And I think that's perfectly fine for the purpose. I think it looks cool. So if you don't want to set anything else, you can leave it at that. Maybe if you want to change the color, you can go under visibility and set the modulate property to a different color, and you can see that changes the line's color. So if you want to use something else, you can always change the modulation because it's a white texture, and you can set the color to whatever you like. But for now, I'll just leave it at white because I kind of like it. And we can delete these test points because we no longer need them. Probably the easiest way to do it is to go to this points property and click on this undo arrow here to erase this point array. Cool. So we can save this. It's a pretty simple and basic scene. We can save this with Ctrl S. And we're finally ready to orchestrate this whole thing we did together in a visual way as well. So the next step in the process is to actually hook this up in the map scene and sort of make some changes to the map scene so we can set everything up correctly. So for now, we can close all the other scenes. And we can go to the map scene or press Ctrl-Shift-O and search for map.tscn if you don't have it open. For now, we can close this animation pane at the bottom, and we can actually get rid of everything here because we no longer need these control nodes. So I'm selecting this button node here, pressing and holding Shift, clicking on the color rect, and delete everything. And we also need to change the map because it's a control node now, but if you remember, we want to scroll this, right? So we want it to be in the 2D space of the game. So we'll right click on this root node, the map node, and click on change type. And instead of a control node, we'll search for node 2D. Right. Then we'll need some other stuff. So select the map as the root node and click on the plus sign to add a child scene. And we'll add 3 new node 2Ds actually. So click on node 2D again and duplicate it 2 times by pressing Ctrl D. We can rename the first one to visuals, rename the second one to lines, and rename the last one to rooms. And we can select rooms and lines at the same time and drag them under the visuals node, right? So we'll have our visuals here, and all the lines and map rooms will be under this one. Okay, now we can select the map, the root node again, and we also need a camera so we can scroll the map up and down. So search for camera 2D. And to make sure that it looks a bit more interesting, I also added a gradient background to this whole map. And to do that, we'll select the map again. Click on Add Child, or press Ctrl A, search for Canvas Layer, double click and rename this to Map Background. And under this Map Background, click on the plus sign again, one last time, and we'll add a texture rect. So we can create this gradient, double click, and rename this to Background. Okay, so we have everything set up. Now let's configure them one by one. So let's start with the background here. Make sure that the Anchor preset is set to full rect, so it covers the whole screen. And for the texture, we can add a new gradient 1D, for example. And if we click on this gradient resource here, we can set the width to something lower to make sure it looks a bit more pixelated, like 50. And you can see those lines appearing there, hopefully. You can experiment with this value if you want to. And if you click on the gradient itself, we can change the colors. So for my starting color, instead of this black, I selected this handle and click on this square here. Instead of black, I'll use this sort of grayish value. And at the end, instead of this white, I use this kind of rusty color, which I have here. Something like that looks fine to me. But again, you can use the values you like. Okay, so we have our background ready. That's done. Our map background, however, is need to set on a different layer to make sure that it's rendered behind everything else. We don't want it to cover the top bar. We don't want it to cover up the icons or all the visuals. So we can set its layer to -1 to make sure that it's behind everything else. Cool. We can move on to the camera next. If you click on the camera, you can see that we have this little pink frame here. And this is what's showing us where the camera is focused now. And we kind of need to change that. So we need to set this offset here. And what we can do is we can offset it by half of the screen's width and half of the screen's height. So the screen is 256, so we can divide that by 2. And you can see that this pink box is already looking right on the horizontal axis. And for the vertical axis, the Y, we can do 144 divided by 2 because that's the size of our screen, and it does cover the whole screen perfectly. Nice. That's all the setup we need for the camera. The rest we'll do from code. For the lines and rooms, one thing we need to make sure of is that we can access them as scene unique. If we were to make any changes to this node hierarchy, we can right click this and say access as scene unique names. And maybe we can modify the orders of the nodes a bit, because when I work with 2D, I like to have the blue ones, the 2D nodes on top and everything else under them. So I can move this map generator under the camera, which keeps things a little bit more organized. And that's the final node setup we need for the map. All that's left to do is to actually hook this up with code. But before we do that, we need 2 new input actions for scrolling. So let's go to project settings, go to input map, and in this add new action text box, type in scroll_up, press enter or click on this add button here, click on it again, and this time type scroll_down, press enter. And you can see that we have these 2 new input actions here with no actual input assigned to them. So click on this plus sign here. And under mouse buttons, we have mouse wheel up, which is perfect. Click OK. And for scroll down, click on the plus sign again. And under mouse buttons, search for mouse wheel down. Click OK. And that's it. We have our 2 new input actions set up, which we can use from code. We can close this window, save the map scene by pressing Ctrl S. And we can hook up everything we've built so far in the maps script. So let's click on the script icon to edit it. And we can actually delete everything from here because it no longer even extends the control class because it's a node 2D. So how does this map script is going to look like? First of all, we'll provide a custom class name called map and make sure that this script extends from node 2D and not the control node because we changed it, right? Then we'll have a constant called scroll speed and also 2 other constants which preload the MapRoom and the MapLine scenes so we can instantiate them based on the map data. Then we have 5 already variable references to the map generator, the lines, the rooms, the whole visuals, and the camera 2D. Basically to all the nodes but the background. Then we have some member variables. We have a map data which serves a similar purpose that it does in the map generator. It will contain all the data. It's an array of arrays, and the inner arrays are arrays of room resources. Then we'll have an integer called floors climbed, so we can keep track of which floor we're currently in. And we also have a reference to the last room we selected, which is a room resource. And we'll also have a variable called camera edge y, which we need to calculate, right? Because we need to know where the end coordinate of the whole map, right? Because it will go from 0 to negative something. And we need to make sure that we have access to this so we know how far we can scroll with the camera. Then what we do in the ready callback is we calculate this camera edge y value, which will be the y distance constant from the MapGenerator class multiplied by the number of floors minus 1. Then we call our generate new map method, which we'll do next, and also call a method which we'll implement later called unlock floor 0, which does what it suggests. It unlocks all the starting rooms on floor 0. But before we do the generate new map method, we also need to override the input method so we can handle scrolling with the camera, right? And what we do is, first of all, we check if the registered event is scrolling upwards, and if it is, then we subtract from the camera's Y position based on the scroll speed we have. And we do the same when we scroll down, but in the other direction, right? So this Y position will be bigger, meaning that we add our scroll speed to the camera's Y position. And to make sure that we can scroll infinitely after adding or subtracting to it, we can clamp the camera's Y position between 0 and the negative camera edge, which we just calculated in the ready callback. Now on to this generate new map method. What we do here when we're starting out with a new map is we set the floors climb to 0, call the MapGenerator's generate map method, which returns an array of arrays, and we can assign this whole map data to our own map data variable and call another function which we call create map to actually initialize the visuals for that map based on the data. Let's see this create map method next. So what we do is we want to iterate through all the rooms we have, right? So first of all, we'll iterate through the current floor, which will give us an array, and then we'll iterate through all the rooms in that specific floor we have. And what we do with that room is we check if it's used or not. And to do so, we'll do the same we did with the map generator. We'll see if that room resources next room's array is not empty. Because if it's not empty, it means that we use it to generate a path and we can spawn that room in our map, which we'll do with a new method called spawn room. But we also need to kind of handle the boss room separately because it wouldn't actually satisfy that condition of having next rooms, right? Because it's the last one. So we need to make sure that the boss room is always spawned separately. And what we do is we, again, calculate the column index of that boss room the same way we did with the map generator and make sure that we call the spawn room method on the boss room separately. Then what we can do is we can calculate the whole map's width in pixels by multiplying the x distance between the different nodes by the width of the whole thing. And why do we need this? Well, because we want the map to be on the center of the screen, right? So how do we center this? If we know that, for example, our screen consists of 1000 pixels to make the calculations easy, we can say that the center of the screen is then 500 pixels, right? But we also need to take into consideration how wide the whole map is. So if the whole map is 500 pixels, then if we were to put it at 500 on the x, that would mean it would be aligned all the way to the right instead of the center. So what we do is we take the whole viewport rect's x size, subtract the map's width from it, and divide this number of pixels by 2 because we want this to remain on both sides of the map in order it to be on the center. And for the y, that's a lot easier because what we need to do is we offset it by half of the screen because we can scroll it anyway. We just want it to kind of start at the bottom of the screen when we first generate the map. The next thing we do is this unlock floor method, which takes one parameter, namely the floor we want to unlock, right? And here what we do, after spawning all the rooms, we iterate through all the children in the room's node 2D node. Why? Because this way we no longer have to keep track of used and unused room spaces in our grid, because we only instantiated the rooms under this node 2D node which are used. So we can save a lot of calculation with this. And what we do is we iterate through all the map rooms, and if the map room's room resource has the same row index as the floor we want to unlock, we set its available property to true. And we'll also provide the method to unlock the next rooms, which we'll use in the run scene when we actually win a battle or we visit a campfire or something. We want to be able to not just unlock a whole floor, but only the rooms which are connected to the current room, right? So here what we do is we iterate through the children of this room's node to the node again. And what we do is we refer back to the last room we visited, right? And if the last room has a connection to the current map room we're in, it means that it's connected to it and it should be unlocked. And if that's the case, we just unlock it. We'll also have two utility methods to show and hide the map. And showing the map means two things, basically. calling the show method on the root node, the node 2D itself, to make sure everything is visible, but we also need to enable this camera 2D. Why? Well, because if we hide the map, then we don't just need to call the hide method on this node 2D, we also need to make sure that the camera is disabled because we don't want to use the camera anywhere else in the project, right? And finally, we have this spawn room method, which is responsible for actually putting down those MapRoom instances when we get the data from the MapGenerator. So how do we do this? First of all, we'll instantiate a new MapRoom, right? And we add it as a child to this rooms node 2D. And then we do a couple of things. First of all, we set this new MapRoom's room resource to the room we want to spawn, and then also connect its selected signal to a callback function, which we'll provide very soon. And also need to call one last method here, which is called connect lines, to make sure that we can actually render those MapLine instances between the connected rooms. And also this will be only used for loading the game later on, but we can provide this functionality now. So what we do is we check if the room was selected previously or not. And if it was selected and it's behind the floors that we have already climbed, it means that we should show the outline around it because we already visited that room earlier. These two lines of code will be only used when we actually load a save game from the previous session, but we can provide this functionality now, sort of thinking ahead. So how do we connect the lines between the connected rooms? Well, first of all, if the room that we are currently talking about has no next rooms, meaning it's not connected to anything else, we can return immediately because we don't have to draw lines between anything. However, if it does, then what we do is we take all the next rooms, all the rooms that this room is connected to, and iterate through them, instantiate a new MapLine scene, add 2 points to that line 2D. The first one will be the room's position, and the second one will be the connected room's position. And then finally, we don't forget to add this new MapLine instance to the lines node 2D container we have in the scene. And finally, we have this callback function when we actually select a room. So what we do when we select a room is we iterate through all the rooms we have and make sure that all the map rooms, which are in the same floor as the one we just selected, are set to unavailable. Why do we need this? Well, because of the starting points, really. If you think about it, when we start the game and we have, let's say, 4 starting points, all of them are available to select, right? Because we unlock the whole floor. But when we actually click on one, we don't want the adjacent rooms to ever be selected on that playthrough anymore. So this is where we actually set them to unavailable to make sure that we can't click on them anymore, only the ones that are connected to that first starting point we selected. And then after handling this, we can set the last room to this one, right? Because if we clicked on it, this will be the last room we visited, increase the number of floors climbed by 1, and actually emit this map exited signal and pressing on the room as a parameter, so the run will know what to do, right? What kind of room we need to show to the player. But that's actually kind of a problem because our map exited signal in the event bus has no parameter defined yet. But we'll fix this when we hook this map up in the run scene. So for now, don't worry about this. This is what we need to do in the map itself. So save this with Ctrl S because that's all there is to it. And let's see how we can test this. And we don't really have to do anything besides running this scene because in the ready callback, we already called the generate map and the unlock floor 0 methods. So in theory, if everything is set up correctly, we should have our full map ready to go and function. So if we run the map scene, indeed we have our map here, right? All of these are available and highlighted and I can scroll up and down. Cool, we have our different icons and scales. We have the boss room at the very end. There's no crossing paths. So all the hard work we did so far seems to be paying off. I can select either one of these and you can see that when I actually select one and the animation finishes, all the other ones are no longer highlighted and I can't click on them, right? And that's exactly what I wanted. Because what I want here is to actually go into battle, and when I want that battle, then I can unlock this one and this one, because these are the only rooms connected to the last room we visited, right? But this is no longer the map's responsibility because we provided this unlock next rooms method, and the run can orchestrate this whole thing as the brain of the whole operation. The map itself is finished. So the final thing to do in this video is to actually hook that up in the run to make sure that we can switch between these different contexts. And just before we do that, we can go back to the ready function and get rid of this map generation because we don't want the map to do this in the ready callback. We can do this from the run when we actually start a new run, right? So we can sort of just grab these lines and delete them. The camera edge needs to stay there because we need to calculate the height of this whole thing, but those lines are not needed anymore because these were just to test if the map is working or not. But since we're hooking up this whole system to the run anyway, let the run handle this when we actually start a new run. So let's save this with Ctrl S and do the final steps together. So before we start changing the run a bit, let's not forget that these signals are no longer in sync because here we want to pass the room as a parameter, but in our events, this map exited signal has no parameter attached. So let's just change this real quick. So if you press and hold Ctrl and click on this map exited signal, it should open up that script and you can see, right? This signal has no parameter, so let's just quickly change this by adding a parenthesis and say that we'll pass a room as a parameter here. Cool, that's all we need from here. We can save this with Ctrl S. And we can go back to 2D view, press Ctrl-Shift-O and search for run.tscn to open it up in the editor. And you can already see that we have our background here because the map scene we instantiated is updated. So we don't really need to change anything in the run from the editor perspective, but there's quite a bunch of changes we need to do from the scripting side or coding side. So let's click on this run script icon here and see what we need to change. And the first one we need to change is actually a pretty big one. We have all of our scenes preloaded here as constants when we want to change the different views. But for the map, that's not right because we don't want the map to be instantiated over and over again because that would mean generating a new map every time we instantiate it. And we don't want that, right? We just want to hide it when we're not at the map view or map screen. So we can get rid of this constant for now. And instead what we need is an already variable reference to the map. So one thing you can do to avoid typos is to actually select this map node here when you're scripting, start clicking and dragging it into the code editor and press and hold Ctrl while doing so. And what it does is it automatically generates this already variable reference for you. Okay, so we fixed that. Now we have an already variable reference to our map and we no longer need to instantiate it everywhere. What's next? Well, the first thing is in the start run method. So we have this little debug message here that we should procedurally generate a map here. And we already kind of know how to do that, right? So we can replace this code with something like map.generateNewMap and map.unlockFloor0. This is what we did in the map ready callback, but we can do it here when we start a run instead, right? Another thing to do is in the change view method. So when we change the view to something other than the map, a battle, a campfire, anything, we actually want to hide the map, right? To make sure that the camera is turned off and we can no longer see the map. So here what we can do is we can call the maps hide map method. And what we also need to do is to provide a new method called show map, because if you remember, for example, when we exit a battle reward here, we use the change view method with the map scene constant to switch back to the map view. But we can no longer do this because we don't have access to the whole map scene and don't want to instantiate it again. But what we want to do instead is just show the same old regular map, right? And we need a method for this. So here what we do is first of all check if the current view has a child or not. Because if it has a child, it means that it's still not deleted that campfire scene or that battle scene or whatever. So what we do is check if it has a child, and if it does, we take the first child and delete it with Q3. And after that, what we can do is we can call the show map method to show the map again and enable the camera, and also unlock the next rooms, because if you think about it logically, when do we want to show the map? We don't have to call this in the beginning because we haven't clicked on any rooms and the map will be visible by default, right? But when we do need to call this show map method is when we exit any other view in the game. So when we exit a campfire, we'll call this. When we collect the battle rewards, we'll use this, right? So whenever we use this show map method, it means that we should unlock all the next rooms available. So the next thing we need to fix are these broken references, which would change the view and instantiate a new map scene. We no longer want to do this. Instead, what we want to do is we want to show the map, right? This is why we created this show map method. So all of these broken references can be replaced with this show map method we just created. Right. And basically that's it. But if we scroll all the way down here, we have our on-map exited callback. And we have this debug message here as well saying to do from the map, change the view based on the room type. And this is what we actually need to implement in order to make this whole game interactable. So how do we do this? First of all, we'll need to fix that callback function, because if you remember, our map exited signal is no longer without parameters. It will have a room resource, right? So let's call this parameter room of type room. And what we do here instead of this print message will be pretty simple actually. We'll use a match statement, which is equivalent to the switch case in other languages. And we say that we want to match the room's type, which is an enum, right? And if it's a monster type room, then we change the view to the battle scene. If it's a treasure type room, we change it to the treasure scene, and so on. And basically that's all the logic we need. And that's it. We're done with the whole setting up things and hooking up things and generating the map. I know this was a bit of a head scratcher and a longer one, but hopefully it makes sense. So let's test this whole thing in action. Save this with Ctrl S. And let's start a new run by running this scene. And immediately you can see that everything is still working like it did before. We have our deck, we have our gold, which we did in the last episode, but we also have our new map here. And we can actually go to battle now. So if I click on this one, it changes based on the selected room. With this match statement, you can see that this is a monster type of room, so we change the view to the battle scene. And we can play the battle just like we could before. And if we finally manage to win that battle, we can collect the rewards, add a new card to our deck, maybe take this blue one, continue, and voila! You can see that all the next rooms are available, they are highlighted, and I can no longer click on the other starting points here. And you can see that this doesn't play this highlight animation. I can't click on it anymore, but it still has that nice little selection circle around it. I can still scroll, I can go to this shop, which will be again a placeholder, but it should work because when I press this go back button, you can see that it has this highlight. I can no longer click on any of those, and I only have one place to go from here. And again, I go back to this battle. So in theory, we can basically play the game now. All there's left to do for us is replacing those placeholder scenes with actual shops, actual treasure rooms, actual campfires, and so on. So that's it for this video, and I guess I'll see you in the next one. Bye-bye.